Hi students, welcome back to the virtual lab of tube physics. Today we are going to do an experiment by using Vernier Calipers. This is the first experiment for 11th graders, and this apparatus, Vernier Calipers, it is used for measuring the dimensions of solid bodies like sphere, cylinder, beaker, etc. with more accuracy, with an accuracy of 0.1 millimeter. Now we can see the important parts of the Vernier calipers. The Vernier calipers consist of, main part of the Vernier calipers is this main scale. Okay? This is the main scale. In this main scale, each one division, small division is equal to 1 millimeter. One division equal to 1 millimeter. And there is another small scale here that we can slide. Okay? This is the one small scale that is called Vernier scale. This is Vernier scale. And this one is the main scale. And there are two jaws here. One is this jaws. This is used for measuring the outer diameter, so outer dimension of object. And this is another jaws. Okay, this upper one. This is used for measuring the inner dimensions, like inner diameter of a beaker. We can measure by using this one. For example, if you want to measure the outer diameter of a cylinder, we can keep the cylinder in between these two jaws and press together, tight contact, then we can do the measurement. And if you want to measure the inner diameter of a beaker, see here, this jaws we have to fit inside maximum, and then we can take the measurement. So the upper jaws are used for measuring the inner diameter, and these jaws are used for measuring the outer dimensions. And also at the back side there is a depth measuring prong here, and by adjusting here we can adjust this one until it touches the bottom of the beaker. So this is used for, this prong is used for measuring the depth of a beaker, and all measurements will be taken from here only. Inner diameter, inner dimension or outer dimension, or the depth of a beaker, all measurements will be taken from this area only, that I will explain. Okay, today we will be doing the first experiment, that is to measure the volume of a given sphere. So all of you write down the aim of the experiment. Aim is to measure the volume of a given sphere. And the materials required, the Vernier calipers and the given sphere. And the first step of the experiment is that we should know the least count of the Vernier calipers. See how to find the Vernier calipers least count. You can see here on this Vernier scale, you can see on this Vernier scale there are 10 divisions. Okay, and when we keep these jaws pressing together each other, then we will see this one. You can see the magnified image of this scale here, over here. And this is the Vernier scale, okay, dark one, and this is the main scale. And now we can see the 10 divisions of Vernier scale is coinciding with the 9 divisions of main scale. So all of you write down, 10 VSD. 10 VSD. VSD means Vernier scale division. 10 VSD is equal to 9 MSD. 9 main scale division. 10 Vernier scale division is coinciding with the 9 main scale division. So we can write down 10 VSD. 10 Vernier scale division is equal to 9 MSD main scale division. Next line. Therefore, 1 VSD is equal to 9 by 10 MSD. 9 by 10 MSD. That is, 1 VSD is equal to 0.9 MSD. 1 VSD, Vernier scale division, is equal to 0.9 main scale division. And we can see from the scale, main scale, 1 main scale division is 1 millimeter. 1 MSD equal to, write down, 1 MSD equal to 1 millimeter. Therefore, 1 VSD is equal to 0.9 millimeter. 1 VSD is equal to 0.9 millimeter. The next line, least count is equal to 1 MSD minus 1 VSD. Least count is equal to 1 MSD minus 1 VSD. That is 1 millimeter minus 0.9 millimeter is equal to 0.1 millimeter. 0.1 millimeter is the least count of the vernier calipers. 0.1 millimeter is the least count of the vernier calipers. Okay. The next step is we have to check the zero error. For checking the zero error, we need to keep these two jaws pressing each other. That time you see the zero of the vernier and zero of the main scale, they are accurately straight. They are accurately straight. There is no gap in between them. So we can say there is no zero error for the device. Usually vernier calipers will not have any zero error. Zero error equal to 0. Now, for doing the experiment, that is to find the volume of the given sphere, first of all you need to draw an observation table as shown here. Okay, draw the table like this. In this observation table, there are 5 columns. The first one is for the trial number, the second one main scale reading, the third one is vernier coincidence, and the fourth one is vernier reading, and the fifth one is the diameter of the given sphere, that is given by x plus y. And we can repeat the experiment. Okay, see how to do the experiment. First of all, we need to keep the given sphere in between the two jaws to measure the diameter of the given sphere. Keep the sphere in between the two jaws and move this jaw and tight it, keep it in tight contact. Then we have to make the measurement. Finding the measurement, as you see the first division of the vernier and where it is coinciding. We can see the enlarged view here. Now we can see here the vernier scale. This is the vernier scale, the small one. This vernier scale is here. This is the vernier scale. In the vernier scale, the first division, it is not coinciding with the 1 exactly. This 1 centimeter. It is not coinciding with 1 exactly, little more than that. But it is also not equal to 1.1 centimeter. So here we can take the main scale reading only 1 centimeter. You can take 1.1 only if this vernier cross this one, or accurately straight or cross this one. If it is before 1.1, don't take it 1.1, it is only 1 centimeter. Or you can write in 10 millimeter. We will do the calculation in millimeters. So this is 1 centimeter means 10 millimeter. Write down in the observation table the first trial, main scale reading 10 millimeter. Then that is x. X is the main scale reading, that is 10 millimeter. Now we will see how to take the vernier coincidence. The vernier coincidence we can find out like this. Out of the 10 divisions on the vernier, only one division will be, one line will be exactly in straight with any one of the divisions in main scale, any one of the divisions in main scale. And that we can see in this enlarged view. So this is the vernier scale. Out of this, you can see they are not in exactly straight, but one division, one line, this is the one line, exactly in straight. One line is exactly straight with the, okay, coinciding straightly, okay. One line is exactly coinciding with the main scale, that is, which division? 6th division is exactly straight with the, 6th division of vernier is exactly straight with the main scale reading. So vernier coincidence is 6. So next column, that is vernier coincidence, write down 6. The next column, that is vernier reading, its vernier reading is 6 into least count. Least count is 0.1. So 6 into 0.1 is equal to 0.6 millimeter is the vernier reading. Then diameter is equal to x plus y. X plus y, that is 10 plus 0.6. Means 10.6 millimeter is the diameter of the sphere. Okay. Again we can repeat the experiment. Now we will repeat the experiment by changing the sphere. Now we have another sphere here. Okay. Again I am adjusting this jaw. Keep it tight contact. Then see the first division of vernier is coinciding with which division of main scale? That is 2.1. 2.1, not 2.2. 2.1 it crossed. So we can write it in millimeter. 2 means 20. 21 millimeter. 21 millimeter is the main scale reading. So what if you write down the observation table, second trial with the different sphere. Okay. The main scale reading x is 21 millimeter. 21 millimeter. Okay. Then Vernier coincidence, out of these 10 divisions, one division will be straight with the main scale, that is here, this is 5. Okay, 7th division is exactly straight. So Vernier coincidence is 7. Then Vernier reading will be Vernier coincidence into multiplied by least count. That is 7 into 0.1, 0.7. That is Y. Vernier reading is Y is 0.7 millimeter. Therefore, the total measurement is here 21 millimeter is X value plus 0.7. So 21.7 millimeter is the diameter of the sphere. Okay, that's the second trial. Now we'll do one more trial with another sphere. So here the main scale reading is, we have here main scale 1 up to 1.5. So we can see here exactly the enlarged view. This is 1.5, 1.6, 1.7, almost crossed. So we can say it is 1.7. We can say it is 1.7, little above that, little more than that. So it is 1.7 centimeter, or we can say 17 millimeter. 17 millimeter. That is X value, main scale reading. Then Vernier coincidence, which line is exactly in straight, that is the next immediate one, that is number 2. Second division of Vernier is straight. So 2 is the Vernier coincidence. Then Vernier reading Y will be 2 into 0.1, means 0.2. That is Y. Then diameter is X plus Y. That is we have 17 plus 0.2. That is 17.2 millimeter. 17.2 millimeter is the diameter of the third sphere. Now we'll find the volume of each sphere. Okay, now we'll do the calculations. As you know, the least count we got here. Least count is the value of 1 MSD minus value of 1 VSD, Vernier scale division. We have one main scale division 1 millimeter, and one Vernier scale division is 0.9 millimeter. So the least count is 1 millimeter minus 0.9 millimeter. The 0.1 millimeter is the least count of the Vernier. Now the calculations here. Okay, we have this much diameters. The diameter of the first sphere we got, that is 10.6 millimeter. Our aim is to find the volume of the sphere. For volume of the sphere, all of you know the equation is V is equal to 4 by 3 pi r cube. This is the equation for volume, and we need the radius only. So for the first sphere, 10.6 millimeter is the diameter. So radius for the first sphere is R1 is equal to 5.3 millimeter. 5.3 millimeter. Okay, so its volume will be equal to V is equal to 4 by 3 pi, we can take 3.14 into R cube, that is 5.3 cube. So we can find the volume, that is 4 divided by 3. 4 by 3 is 1.33, so we'll take as 1.33 into 3.14, the pi value 3.14, and into cube of 5.3. So 5.3, I should multiply 3 times. 5.3 again 3 times, so that is equal to 621. That is the volume of the first sphere is 621.7. This unit will come in millimeter cube. We did the calculation in millimeter, so the volume is in millimeter cube. 621.7 millimeter cube is the volume of the first sphere. The same way we can calculate the volume of the second one. For the second sphere, radius R2 is equal to, it is 21.7 is the diameter by 2. Radius is 10.85 millimeter. Okay. Then volume V is equal to 4 by 3 is 1.33 into pi value 3.14 into cube of the radius, that is 10.85. This one was bigger sphere, 10.85 cube of that, 5334.2. So 5334.2 millimeter cube is the volume of the second sphere. Now for the third sphere, radius of the third sphere R3 is 17.2, 8.6. Radius of the third sphere is 8.6 millimeter. So its volume will be equal to, volume of the third sphere is equal to 4 by 3, that is 1.33 into pi value 3.14 into 4 by 3 pi r cube. R is 8.6. 8.6 is equal to 2656.2. 0.29 we can round off to 0.3, so 2656.3 millimeter cube is the volume of the third sphere. Okay, thank you.